Okay, it's time for part 9 of my LinuxCNC HAL tutorial. The grand finale, the piece de resistance, the dick in a vice, the torch height controller. Okay, so let's begin with a quick rundown of the takeaways from this series. We've got HAL, the hardware abstraction layer in LinuxCNC, and it lets you control pretty much every single thing on your machine, way beyond what you can do with plain old G code. And HAL is set up through a series of configuration files. The way I like to think of it is that these files are basically defining a software emulated PCB. So, in real PCBs, you've got all these surface mount components, things like LM315s and LT640s and all those little chips that go on a board. And in HAL, you've got HAL components, right? Things like motion, stepgen, THCud, logic, OR2, AND2, pyvcp, all these components we've been using throughout the series. And then on a PCB, you've got traces and wires and stuff like that. But in HAL, you have net commands. And the net commands define the software traces between HAL components. And every net gets a signal name. Signal names are just like having a color-coded wire or a label on a trace of a PCB. So that's really, all the HAL files are. Just think of it that way, and you'll have it, have the concept pretty, down pretty well. The Step Comp Wizard will set you up with a basic set of HAL files. And when it's time for you to build on that and add more and more to your machine, then the man pages are definitely your friend. So for example, you go to the command line and do man motion, and that pulls up the manual for the motion component and all the HAL pins that come along with that. There's dozens and dozens of HAL pins. So yeah, when I'm working on my stuff, this is definitely my go-to quick reference. For more in-depth information on LinuxCNC in general, you've got the PDF docs I've also shown a million times already, right underneath here. They come pre-installed on every installation of LinuxCNC, and it's like 745 pages of PDF docs. Very, very thorough. I've also shown the use of Git quite a bit in here. This is totally an optional part of things. You don't need to use this by any stretch, but if you learn the very basics of just like, git add, git commit, right? Just those ones, and then like git k and git log to go back and look at the history. It's very helpful. Okay, it just helps keep track of the configuration files and the changes you made, when you made them, and why you made them, and more importantly, when it breaks, what broke it, and how do you go back and revert that change so you can get your machine running again. Okay. And another bonus, it makes it easier to publish stuff up on GitHub so you can share those configuration files with other people and help us all learn how to make better machines. Another handy tool that I don't think I've shown yet is halcmd. And this is another one that's useful when you're building out the machine. Basically lets you run commands that you have in your HAL files one off at a time. And if you do it with, let's see, the FK options, so halcmd-FK, that stands for fuck, because you're working with HAL and it can be a bit frustrating. Anyway, -FK, and it gives you a prompt that actually has tab complete. So when you're here and you hit the tab, it gives you a list of different things you can do. So you can like load user, and then it gives you an option of things you can put on load user. Stuff like, HAL input and HAL UI, things we've seen before. And that just kind of helps you figure out what, what the options are for, building out your configs. Personally, I didn't use it myself, but I just want to let you know that it is a tool at your fingertips and you might find it handy. When it comes to debugging, in real life, you've got ohm meters, right? And in HAL, you've got HAL meters. These little guys where you can, pick which signal you want to watch, and it gives you a display of what the signal reads right now. Very, very convenient, just for monitoring machine as it's going. And you can pick from any pin, any signal, any param in all of your running HAL instance. When debugging a PCB, usually use an oscilloscope. When it comes to HAL, use the halscope. It's another tool I'm pretty sure I haven't shown yet, but I did want to cover it at least briefly because it's a very useful tool to have. Just like an oscilloscope, you've got channels, you hook up probes, those watch signals. But following the same parallels as before, these probes are software probes going to HAL signals. So you can see channel 1 is hooked up to THC up, channel 2 to torch down, and channel 3 to the THC offset. And the way this is set up right now, it's reading 4,000 samples at a 1 kilohertz rate. And I think by default, halscope can read up to 16,000 samples. So I could have the 4 channels then reading 1,000 samples per second for up to 4 seconds. And then if you change the sample rate or the number of channels, you can kind of play with that and get either shorter, more high resolution periods or longer, lower resolution periods. And it's not like it gives you a massive plot of everything, but it gives you a short view of that moment where hopefully you can see what is going wonky with your CNC, right? You make it trigger at the moment you need, to catch that bug, and you can watch on every iteration of either your servo thread or your base thread what was happening and what signals being received that made your machine, do something that you weren't expecting. So here I was just watching how the THC worked, because the LEDs here are great, the halmeter is great, but being able to see it, each loop of the servo thread is even better. So you can see when I began the cut, there's a little blip where the torch height or torch up signal was being sent, and then after that it was level for a moment, and then it kind of began going down. Now the plots here where it's low, that's the false in HAL, right? In the way it's false right now, and then when it goes high, that's it being true. So you can see here by how solid blue this is, that was actually the signal going up and then right back down immediately. And it wasn't continuously up, otherwise you'd see like a solid step like that. But it's going up and down really, really fast because it's continually catching up and then stopping that signal and then waiting a moment and then saying, oh, I need to go down further, and kind of like sending that as a quick series of pulses, kind of like Morse code in a telegram, right, that way. And that's being translated then to a fairly even and downward slope on the current offset. Now you might wonder, when this down signal, goes true, why is the THC up signal not going false? And why are they not like swapping in sync, right? You'd expect maybe, as this one goes high, this would go low, and then they'd swap places exactly. But you're seeing places like where both of them are false. Well, that's because back when I made my torch height controller, I set the threshold on that to allow for a little bit of a dead zone. Whereas if it's close enough to being on the spot, then it just lets it stay. Because I was able to find by looking at halscope that if you made it really work hard to keep exactly on the money with the voltage that you set in that torch height controller, it would end up overshooting continuously. And this offset, rather than being a smooth curve that follows the track, it would end up seesawing pretty awfully, like up and down and up and down. Because the moment you go all the way down, you start sending signals to go back up again, and you continually overshoot. So by building a bit of a dead zone in there, where I said it's good enough to be within like a volt or so of the target setting, that made it react much more smoothly. In fact, maybe later I'll go back and reflash the older version of the code back on the Arduino, so I can even show you that in a different example of how the halscope works. But yeah, the slope on the offset is pretty smooth, and you can see it's measured out in increments of 5 thou, and it's gone down about 3 divisions, so that's about 15 thou of total offset applied over the course of that cut. And then by probing at the start and the end, I was able to see that the plate actually did slope by about 15 thou over the course of the cut, and the story checks out. That's exactly what we want to see. Anyway, things should be coming together pretty well for you by now. So let's take a look at the changes I made at this step in the HAL, and we can run through this pretty quick and then get on to doing a demo. As usual, we're going to use git k and the diff mode to look at these changes. Let's crank up the context lines a bit and start looking through the first commit. So I changed a few things in the THC HAL file. Up at the top here, it's mostly just changes for readability, just reorganizing the way things go. But one real change is taking the OR2, where we used to only have one of them here, and now I've incremented the count to have 3. So we have a couple more OR2s that we also need to add to our servo thread right down here. And everything else just moving around to make it easier for me to work with and read. The probing, nothing here changed. And moving down to the torch height control area, we fixed a few things in the velocity control section. So we used to set the thcud velocity settings all to 1, just to let us do the manual torch height control. Now we've done the proper hookups for all those connections. You take the motion current velocity, hook that to THC current velocity, requested velocity to requested, and we're setting the tolerance now to 30, just hard-coded for the time being. What this does, as I've said before, is it enables corner locking. Basically, as the torch slows down to go around a corner, that usually makes the kerf of the cut get wider. That makes the voltage go up, and then that makes the THC think the torch has to go further down, which is not what you want. It's just, reading erroneously because you're slowing down to go around that corner. So right now, as long as you're doing at least 70% of the target speed, the torch high control will be enabled, and otherwise it will stop for just a moment until the torch gets back up to speed. So now that we're not doing the manual torch high control, that Xbox controller, we want to do it the correct way. Going a bit further down, then at the very bottom, I did the changes that make the Arduino THC do its thing, right? So that's already sitting by the plasma table. I've got it wired up between 2 pins on the Arduino, and then the pins, 12 and 13 on the parallel port board. So as I showed in that Arduino board and software overview back in like August, September, in that time frame, I have an optocoupler on that board, and then pin 12 on the parallel port board goes all the way to the optocoupler, and then to the up signal on the Arduino THC, and then the other end of that goes back to ground. And then similarly for pin 13. So then by using the pin 12 NOT, we're able to check and see when the optocoupler being activated makes pin 12 get grounded, and then read that as the torch up signal. And both that pin 12 and then the Xbox X button are used as input to the OR, and either one is allowed to send a THC up signal. And then likewise here for pin 13 and THC down. Now that does mean that both these, the Xbox controller and the Arduino, work as options for torch high control, and that you could, in theory, hit the buttons and make it like fight the Arduino while your plasma is running. And the easy solution to that is just don't do that, right? just don't. But I wanted to leave both of them set up as options in case for any reason I couldn't get the Arduino one to work one day, and I just wanted to use manual torch high control to simply get a job done. I did actually have one instance where this happened because an errant splash of water from my water table went and killed the power supply that my Arduino THC was using. I gotta fix that up a little bit more. There's some work to do there. But yeah, I left both as options just in case you need the manual torch high control still as a backup. And then also, it's an example, again, of all the things you can do with your HAL. Moving on to the next commit, we're adding a couple of pyvcp indicators. So over in the XML file for that pyvcp panel, we've got, an LED pin for our up and an LED pin for down. In the THC file now, I went and added a couple more of these and 2 components. And as I said before, these all get included here because you can only do a load RT in a component once. So you gotta load all of them the first time, even if you're using it over here in the PostGUI HAL file much later. You can get around that by using the HAL 2-pass option in your INI file, but I personally have not gotten that far yet, so I just make sure to load this up good and early, and then also add the AND2 to the servo thread. And over here in the PostGUI HAL file, we're just connecting the THC up signals to the spindle on signal, and then feeding that to the LED. Now, what's the reason for this? Well, basically, while the torch is not running, it's putting out 0 volts on the THC. And that was making my Arduino read, 0 volts, which would be way below the setting of like 130 volts, whatever I would set it to for the torch high controller. Basically meaning that the entire time my machine is on, the pyvcp up LED here would be lit up green, because it always thinks it's low until the plasma torch is actually running, right? Because it's always reading out 0 volts. So by having it only display when the M3 command is active, then it just stops that little nuisance. Of course, I did realize later that I programmed my THC, right? That's something that I personally coded, so I can always program it differently. And then I went back and I changed it now so that when the torch is off and it's reading out 0 volts, it just sends no signal at all. That way it actually solves this problem. But I don't know, if you have a Proma or something, it might still be sending that up signal all the time. So if you want to just shut the LED up, here's how you do it. In the THCud component itself, it's also checking to make sure the torch is legitimately on before it does torch height control. Just the LEDs don't have that, so we add it after the fact right here using the N2 component. Let's see, and then moving on to the final commit. This is where we make use of some of those changes we made back in part 8, where we did some customizations on the THCud component. So if you haven't caught that, the changes here will not be working for you, so you go back and watch that video first. So we're adding a few more things to our XML file for that panel, namely the entries, so you can put in a custom velocity for THC, and then also change the velocity tolerance and read out your offset. Remember before, these two things were hooked up to parameters in the component. So you can modify them in HAL by having a set p command set the parameter, but you couldn't do it while the machine is already running it, to like restart LinuxCNC each time, and that's kind of annoying. So now we have a, what's it called? Spin box, yeah, spin box. It'll let us set both the correction amount and the velocity tolerance. And then we can also read out the offset, which before was not hooked up to anything, and we fixed that in part 8 and hooked it up, so now it'll let us read how far the THC is telling it to move. And that gives us the panel as we see it here. So right now it's just defaulting to 30 for velocity tolerance like we did before, but we can always change that now while the machine is running, to whatever we want. Then in, let's see, the THC HAL, we take out that part where we hard-coded this to 30, and we take out the correction velocity. And then in the post-GUI HAL file, now we make those connections between the pyvcp pins and the THCud pins. And then this one here as well, from THCud back to pyvcp to read out the offset. So here's my torch height controller, and I wouldn't put the shitty firmware back in this Arduino, so there's no slack in the reading for the voltage. That way, if it isn't sending the signal for torch up, it's going to be sending it for torch down, and vice versa. It's always sending one or the other. And in a moment, when we run the torch, we will see just how badly this performs. There'll be a lot of seesawing. It'll be obvious both in the motion of the z-axis, just visually, and especially so in the output of halscope. Then I'll put the good firmware back on here that has a bit of a dead zone between the two, so you can see how that kind of buffers it and makes for a much smoother motion, how much better that performs. Now that the board is in front of us too, I can point out these two little black chips, which are the opto-isolators that we use to send signals from the Arduino to LinuxCNC without ever physically connecting this board to the parallel port breakout board. That's because an opto-isolator isolates the two using light, opto-optics light, you get it, right? And the point of that is that it keeps any possible fault on this side from coming back to the computer and possibly frying it. And that's important because, this is hooked up to a plasma cutter that puts out 300 volts DC. So at some point, you might have a high voltage here that, crosses the wire by mistake, and then it can fry your computer. And just keep it from doing that, we have the opto-isolators. And there's a pair of pins on the Arduino that controls this pair of opto-isolators. And basically, when you activate that, it connects the two pins on the right-hand side just using that signal of light. So it kind of acts as a switch on this side here. And these three wires then come to this screw terminal block where we've got a solid green, a solid brown, a white and green, and a white and brown. And the solid green and the solid brown come together on this one here, and then it goes back to the ground on the parallel port breakout board. And then the white and green and the white and brown each go to pin 12 and 13. I actually forget which is which, it's not terribly important, but they go to each of them. So basically when you activate an opto-isolator, it will then take that respective pin and then draw it through to ground. All is coming through this side here without the signal ever having to come back on this side of the board. So it keeps it, all cleanly separated, that and that. So yeah, now I think we can run this and show you how badly it works. So I get the cover back on here. And yes, this is the cover I use. No surprise that with that and my water basin that I might, I might have shorted that power supply I mentioned before. Yeah, I got some cleanup work to do in this thing still. But, I do it in my free time, and I either have time to make videos or make the CNC pretty. So, take your pick, right? Now, let me get my safety squints on. All right. And we can run this. I'll do a little probe first, and I'll hit the button to collect the halscope while this is running. And look at the flag at the top, right? That flag waving back and forth, and you see how it gets worse and worse. How the amount of change there got bigger. And then if we go to the halscope for this, come on, quiet you, quiet. So the purge on that thing is the most annoying fucking thing ever. Anyway, so now here's the halscope output, and you can see, basically, if the signal for torch up is high, then this one's low, and like they swap cleanly one and the other. And what that ends up doing is taking the offset and makes it seesaw further and further as you overshoot more and more each time. So that is not what you want, and halscope lets you see just how badly it's operating. Now, give me a moment. I'm going to put the good firmware back on. We'll run it again and see how much better it works. And I missed hitting the button. Shit. And again. And then now here we have a much more even and smaller amount of offset applied. Come on, stop it. All right, so here we have a much more even and smaller amount of offset applied. And you can see it kind of followed along with just the natural irregularities of the plate. Because hot rolled steel plate is kind of shit. But this, it makes up for it. Whew. 9 videos. That should have you pretty well covered as far as HAL's concerned. So with that done, a few requests from me to you. Firstly, the LinuxCNC guys have spent a lot of time making a pretty damn good tool. But as far as I'm aware, they explicitly do not take donations on their website. And the reason for that is they don't want some company coming in with a whole bunch of funding and holding them hostage with the money. And I can respect that. LinuxCNC, it's a free and open source project, and they want it to stay that way. They want it to stay community driven and not run by a company. So you can't donate to help them out, but what you can do is build your machine, take your configuration files, slap them up on GitHub, maybe shoot a quick video showing some of the features it has. Nothing this detailed. None of this 5 hours of crap I filmed. Just a quick 2, 3, maybe 4-minute video explaining how it works, and then put that in a comment down below. I'll take some of those and put links to them in my video descriptions, and I'll also up my GitHub files. And that way, when people are looking to build their own machines, they know where to look for more examples and more inspiration. And best of all, it doesn't cost you anything. On the other hand, if you do want to spend some money, I have gone and made a PayPal account for the channel, so the option to donate at the link below, though there is no obligation that you do so. And the way I see it, these videos of mine are just my donation to LinuxCNC. But if you want to pitch in $5 or $10, I'd appreciate it, and that'll just help me buy more hardware to keep making more videos for the channel. Because there is still tons of shit to do. There's using Mesa hardware and servo motors and building the full water bed for the table, upgrading the gantry rails, running unstable releases of LinuxCNC, getting going with Glade VCP, building a mill, building a lathe, upgrading the K40 laser cutter so it isn't shit. Just so much stuff. I've even gotten into aluminum casting lately. I bought a small pottery kiln. I've been using that for doing some small aluminum melts. And I want to build a bigger upgraded electric kiln and shoot video on that too. And then that way I can get into casting gun parts. I mean bike parts. In all seriousness though, I do want to get into building bikes later on this year as well. There is just tons and tons of shit to do. So anyway, I'm going to get back to work on all that. And until next time, peace.